So in this lecture I am going to talk about time invariant systems and time varying systems. Before that, let us recap what we discussed in the last lecture. So in the last lecture we were considering the classification of systems and networks. So we saw the difference between a static system and a dynamic system. That means a memory system and memoryless system. And also we discussed the difference between a linear system and a non-linear system. Basically, we said a linear system obeys the principle of superposition. Okay, so that is superposition and additivity. Okay, so it says that if the linearity properties like a times x1 of t plus b times x2 of t together gives rise to a times y1 of t plus b times y2 of t. This is the linearity property. So as I said, if you notice, the linearity implies two principles. First one is homogeneity and the second one is superposition. Okay. So the homogeneity says that if the input is multiplied by a constant like a times x of t, then the output also multiplied by the same constant a times y of t. So that's what homogeneity says. So if x of t multiplied by a, then y of t also should be multiplied by capital A. So this is an important property and important corollary. That is, if a is equal to 0, okay, then the output should also be 0. So that's what homogeneity says. And the second one is superposition. So the system is linear, it obeys both of them, homogeneity and superposition. There are systems which obey homogeneity but not superposition. So they are non-linear systems. Similarly, there are systems which obey superposition but not homogeneity. Again, such a systems are again non-linear systems. Therefore, a linear system is one in which homogeneity and superposition, both principles are valid, both principles are satisfied. And one of the important outcomes of this is that zero input for a linear system should lead to zero output. So that is the homogeneity property. If the input is 0, then the output also should be 0. It is, but this condition is not sufficient, because 0 input leads to 0 output only implies homogeneity. It does not imply superposition. Therefore, this homogeneity condition is only the necessary condition. It is not sufficient condition, okay, but not sufficient. Homogeneity. So homogeneity and superposition are necessary and sufficient conditions for linearity, which means that if a system disobeys or violates one of these principles, it is non-linear. And a very simple test would be, first thing to do for a given system is first check out whether the 0 input lead to 0 output. So the first question one should ask is, does the 0 input lead to 0 output? If it does, then you proceed with the further testing, not otherwise. If it doesn't satisfy this homogeneity property, then why do you go for superposition? You stop it. Therefore, if 0 input does not lead to 0 output, then the system is non-linear and you can stop further testing. So you don't have to test superposition. And as I said, for continuous time system, it is governed by linear differential equations. Okay, it is the equation governing the performance of linear system and non-linear system also, and this is what we proposed okay, in the last class. Now in this class, let me start with a discrete time system, the same linearity principle. So within a bracket dt systems. Okay. So on the other hand, if you are talking about a discrete time system, naturally now the signals will not be functions of continuous variable t. Now the variable is n here. Okay. So here their functions have a discrete variable, and that discrete variable is n. Okay. Now then the statement will be carried over here. It is very similar to the statement which we stated for continuous time system. Let us say if the input x1 of n gives rise to an output y1 of n, that means what? You take a system dt system and give the input x of n, let me say x1 of n, and the corresponding output is y1 of n. Now you take that same system once again, you take the same system. Now the input is some arbitrary input x2 of n, and this time it gives y2 of n. Okay. Then if the system that is discrete time system is linear, then a times some constant x1 of n plus b times x2 of n, you add these two guys together and give it the same discrete time system. It gives rise to a times y1 of n plus b times y2 of n, and this a times y1 of n, b times y2 of n should be equal to, let me write down here, sum of these two guys like this. Okay, sum of these two guys. Separately you consider find the output y1 of n and y2 of n, multiply y1 of n by a, multiply y2 of n by b, then add these two guys, and that should be equal to this one. Then you say that system is linear. Okay, that discrete time system is linear. Now the input output relationship of a continuous time linear system will be described by linear differential equation. Continuous time system. Okay. So similarly, discrete time system is described by a linear, not differential, it is difference equation. Okay. So now let us look at some examples of equations pertaining to linear systems. Okay, the first example that I would like to consider is 4 times second derivative d square over dt square times y of t plus 3 times dyt by dt plus 3 times y of t is equal to 2 times x of t plus 5 times derivative of x of t, first derivative of x of t. That means what? You have a system We don't know whether the system is linear or non-linear. Let us see, find out. The input is x of t and the output is y of t. Therefore, x of t indicates input variable and y of t indicates output variable. Now look at here, all the coefficients 4, 3, again here 3, again here 2, again here 5, okay, are constant. So this is certainly a linear differential equation of order 2 because it has second derivative order 2 with the constant coefficients. Therefore, this is an example of a linear system. Okay, so this equation corresponds to a linear continuous time system. Now let me take one more example for a discrete time system. Now since it is a discrete time system, I am going to write down difference equation. So y of n plus 2 plus 3 times y of n plus 1 plus, let me put 4 here, 3 times y of n is equal to 6 times x of n plus x of n plus 1. This equation characterizes a discrete time system. The input to the discrete time system is x of n and output of the discrete time system is y of n. Again, if you look at this equation very carefully, it has constant coefficients. Here 4, 3, then again 3, here 6, and here the coefficient is 1, of course. Okay, so the coefficients of the various output terms and input terms are constant. Therefore, this is again a linear difference equation with the constant coefficients. Now let me take another example. Now this time I have 4 times t times d square, let me say dy over dt plus 2t square times y of t is equal to 6 times x of t plus 5 times d first derivative of the input d by dt. Now here we have the coefficients of various derivative terms as the functions of time. See, I have constant, also functions of time, and here also the time is square, t square, and this is 2t, and here it is constant, and here also it is constant. So the coefficients are 4t, 2t square, 6 and 5. As I said, this is also an equation pertaining to a linear system. Why? Because the coefficients are either constant or functions of independent variable. Function, this is like the coefficients are either constant or independent variable. Okay, so one can easily manipulate these equations, and we can show that these equations satisfy superposition principle. So if you have a linear system, it doesn't mean that the differential equations should have only constant coefficients. So even the coefficients can be functions of time, that is functions of independent variables. So this is also an example of linear system. Now the same equation you can write down for a discrete time system, like a discrete time system like would be something like this. I can translate that, this one, like 4 times n times y of n plus 1 plus 2 times n squared times y of n is equal to 5 times x of n plus 6 times x of n plus 5 times x of n plus 1. So you see here the coefficients are not constant again, but functions of time. These functions of time are like it's an independent variable. So either it is constant or functions of time. 6 times x of n. Therefore, again this is a linear equation with constant coefficients or functions of independent variable. Okay. So essentially, to summarize, we have looked at linear systems. Therefore, these are the examples of equations which pertain to linear systems. Now let us talk about non-linear systems. The system which does not satisfy or disobeys superposition and homogeneity, then you call that systems are non-linear systems. Okay. So in non-linear systems, the coefficients are not necessarily constant. Not necessarily constant, first point, or coefficients are not necessarily functions of the independent variable. Okay. So that's what we mean by non-linear system. For example, let us take an equation, let's say 4 times y of t, then dy by dt, first derivative of the output, minus 6 times y of t is equal to 2 times x of t plus 3 times x squared of t. So you see that here y of t is multiplied by derivative of y of t by dt, and also you have an x squared term here. Okay. Here the coefficient is not constant. Of course, you have constant here, but again you have one more extra term, that this term is dependent variable, right? Dependent variable. So the coefficients are constant, but also it has dependent variable. So the factors x squared term and this y of t, which destroy the linearity of this equation. Therefore, this is non-linear. Let me take one more example for discrete time case, like y squared of n plus 2 plus y of n plus 1 plus 3 times y of n is equal to, let's say, 6 times x of n. Now this y squared of n plus 2, I can think in terms of y of n plus 2 multiplied by y of n plus 2 like this. Now this is multiplied by another dependent variable. Okay. Now the coefficient is not constant, the coefficient is y of n plus 2. Look at here. Okay. So the coefficients being y of n plus 1, n plus 2 and multiplied by y of n plus 2. So this is a square term that is involved here. So this fails to be linear difference equation. Okay. So that's all about linear and non-linear systems. So the next category of classification that we will talk about is the difference between time invariant. This is very important property, time invariant and a time varying system. Okay. Sometimes time invariant means people call constant parameter system. the parameter of the system will not change with respect to time. That's what we mean by constant parameter system. And this is time varying system is also called a variable parameter system. When I say variable parameter system, the parameters of the system will vary with respect to time. So conceptually, a system is time invariant if the behavior and characteristics of the system are fixed over time. For example, if you take an RC circuit, like this is C, this is R, and this is Vs, and this is I. Okay, and this system is an example of time invariant if the resistance and capacitance values are constant over time. Suppose let us say if R equal to 100 ohms, then this 100 ohms would be the same either you measure today or tomorrow or after 1 year, and let us say C equal to 1 microfarad, and the same 1 microfarad will be there today or yesterday or tomorrow or whatever it is, or even after 1 million years. Then you say that system is constant. Then you say that system is like a time invariant system. That means we would expect to get the same results from an experiment with this circuit, either you do the experiment today or tomorrow or any time. On the other hand, if the values of R and C are functions of time, R is a functions of time, then C also functions of time. C is function of time and R also function of time, then the output will change with respect to time. Okay, so we would expect the results of our experiment to depend on the time at which we run it. Okay, the property of time invariance can be described very simply in terms of signals and systems language that we have introduced. So specifically, a system is time invariant if a time shift in the input signal results in an identical time shift in the output signal. As I said, also this time invariant system is called a constant parameter system. Constant parameter system. In other words, the parameters which characterize the system and the various components which constitute the system are constant with respect to time. The parameters of the system will not change with respect to system. It is always constant, whether you take the system and get some output or you take the system after 1 year and again do the experiment, you will get the similar result. So therefore, most of the electrical network will function as like constant parameter system. For example, if you buy a mobile phone and the mobile phone is very good today, and if it is not good tomorrow, then nobody will buy that mobile phone, right? Therefore, your mobile phone is time invariant system, constant parameter system. Okay, either you make a call today or tomorrow or this evening or this morning you might have called somebody else, or yesterday you called or yesterday you used, or you may use the phone after 1 year, the system output will not change. Output will not change in the sense whatever the input give that will be affected, that will not, I mean the system will not give any its own contribution. Okay, so if R, L and C are now fixed with respect to time, then you can use those components and you can build some circuit, and that is called constant parameter system. On the other hand, suppose you have a device, okay, in which an inductance or resistance or capacitance is continuously changing with respect to time, then it becomes a time variable system. For example, if you take carbon microphone, so in the carbon microphone, depending upon the input signal, acoustic pressure, the resistance of the microphone may be changing. So that becomes a variable parameter system or time variable system. Of course, it should be time variable, otherwise then it will not give the right output. For everybody's voice, it has to model. So variable parameter system is also sometimes referred to as time variable system. Generally, we will be interested in talking about sometimes time variable systems and sometimes time invariable systems, okay, with respect to linear system. So that is because that's the main focus of our work. So let us look at some equations here and see whether they are time varying systems or time invariant system. So the first one is 4 times d square y of t by dt square plus 3 times dy of t by dt plus 3 times y of t is equal to 2 times x of t minus 5 times first derivative of the input. Okay, and let me take one more example for discrete time. Y of n plus 1 plus 3 of y of, let me call this n plus 2 and this is n plus 1 plus 3 times y of n is equal to 2 times x of n. Now, if you observe here in these two equations have the derivative terms with constant coefficients. Constant coefficient, this is constant, this is constant, this is constant, and this is also constant. Similarly, for difference equation also, here the constant is coefficient is 1 and here 3 and here 3 and here 2. Okay, so this is the characteristics of a time invariant system or constant parameter system. See, the parameter is constant here 4, 3, 3, 2, 5 and here 1, 3, again 3 and again 2. On the other hand, if you consider this equation like 4 times t times first derivative of the output plus 2t square times y of t is equal to 6 times x of t plus 5t times, not t, 5t times, 1 second, 5 times d by dt. Take one more equation for discrete time systems, n times y of n plus 1, 2 times y of n is equal to 5 times x of n plus 1 plus 6 times x of n. Okay. So, in these two equations 3 and 4 we have coefficients which are functions of time. See, here it is functions of time t and here it is t squared and here it is n. So, these are time variable systems. Okay. So, these equations describe the operation of time variable systems 3 and 4. The importance of distinguishing between these two systems are the solution of, let us say, these equations 1 and 2 is much more simple. You can easily find the solution for this guy. Okay, but on the other hand, if you take this time variable system, the solutions are not that much easy, because the time factor t is involved here, and here the time factor n is involved. So the analysis of time invariant system is far simpler than what it would be in the case of time variable system. Now let us consider continuous time system. Okay, now let us try to understand a little more deeper about time invariance property. So if you have take a continuous time system, if you have an input, say x of t, which gives rise to an output y of t. The succinct form, it is denoted like this: x of t, put an arrow mark, and y of t. Then suppose the same x of t is delayed by or translated in time by a certain interval. Let us say delayed means I already told you how the delayed operation would be: x of t minus some time delay td. Okay, now you apply the same input, which is delayed by td input, to the same system, same continuous time system. Now the output would be y of t minus td. So this must be equal to the delayed version of this guy. This one, delayed version of this one. If they are equal, then you say the system is linear, the system is a time invariant system. Okay, no matter what td you have. So if x of t gives rise to y of t, then x of t minus td gives rise to y of t minus td. So this is a condition for continuous time system. Then let me talk about discrete time system. Okay, for a discrete time system, if you have x of n, which gives rise to y of n, which gives rise to an output y of n, and if you consider another input signal, same input signal, which is the same as x of n, but delayed by n units, capital N units, n minus capital N, and this gives rise to the output y of n minus delayed by the same amount of delay. So whatever is occurring at n is equal to 1, let us say n is equal to 1, the same thing occurring in the output also, corresponding output will be like whatever is occurring at let us say x of n, whatever is occurring at n is equal to 1, the same thing occurring at now x of same thing occurring here at n is equal to 1 plus capital N. See, originally something occurred at n is equal to 1, now the same thing is occurring at n is equal to 1 plus n, that is it. That means you are translating bodily shift. So the proper way to call is bodily shift. So that means the response will be shifted by the same amount, but the shape of the response will not be changing at all. So that is a very important point that we should remember. So let me illustrate this by means of some figures. Let us say my input is like this. This is my input x of t, let us say. okay, CT system. Now the output of the system is it is like this, then like this. This is my y of t and time t. Now what I will do is I will shift the input by TD units, some random amount of time. I am sorry. Now it is like this. Oh my god. Like this. Same input, but it is shifted by the amount of TD. Now give to the same system, CT system. Now the output will be shifted by same amount of delay. Like this. Then such a system is called a time invariant system. Okay, so this x of t gives rise to this y of t and this wave shape, this waveform. Then suppose I delay the signal by TD units. This one is x of t minus t suffix d. So instead of 0, here it starts at 0, but here it is starting at t equal to t suffix d. Okay, if it is a time invariant system, we are sure that the output will be the same. See, the shape does not change in the output. Look at the shape, same shape. Here also the same shape, but now it is delayed by the same amount of time. Okay, it starts a little later. The same response, same wave shape, except that it is delayed by the same amount. Here delayed by this much amount of time, and here also it is delayed by the same amount of time, but its shape does not change. That's what we mean. So there is a feature of time invariant systems, and this is a very useful feature, as we would see later on when we talk about impulse response of an LTI systems, linear time invariant system. There we will study convolution integral for continuous time systems and convolution sum for LTI systems. So this convolution integral and convolution sum, these two formulas are derived based on the linearity of the system and the time invariance property of the system. So these two are very important property. On the other hand, if I take let's say the input is like this, same input give to the system, then it gives like this. I am just drawing a free diagram, so let me draw it properly. Like this. Then if we delay the signal by some random amount of time like this, now instead of this much delay, it is giving some other delay, and the shape also changes, like something it is giving like this, like that. So then the system is non-linear system. let's say this system output like this, like that. So this is non-linear, sorry, time varying system. At one time it is giving one type of response, and the same input. See, you are not changing the input. The input is delayed, okay, from the previous one, but the output is different because the parameter of the system is not constant with the time. So at this particular time Td, the parameter of the system is something else. So based on that parameter, you are getting this response. Therefore, this system is time varying system. Now, in the case of discrete time system, let us say we have an input signal x of n, and x of n is function of discrete variable. N is a discrete variable. What I mean is, it will take the integer values. Now, x of n gives rise to y of n. Of course, discrete time signals will have values only at discrete points along the time axis, discrete points like this. In between the points, you do not have no values. Okay. So along the time axis, so the interval between 2 points may be any arbitrary value depending upon the system. See, the interval between one point and this point, this can be 1 second or 1 millisecond or 1 microsecond or 1 nanosecond or 1 minute or whatever it is. This interval can be anything, but you have the values only at integer points. Let us say for integral values of n, you have a sequence of values x of n, and the corresponding corresponding values of y of n are occurs at corresponding value of y of n also occurs at discrete values of n. Now let me take x of n as follows. Let us say I have sequence like this. Let me take 5 pulses like this. Let us say this is n and this is x of n. You give it to a system, now discrete time system, and the output is I am getting like this. I am getting the outputs like this, like this, and like this. So there are 4 values I am getting. Maybe the last one I will write out here. Let me select that 0, 1, 2, 3, and this is n 0, 1, 2, 3, 4. Now you delay the sequence by some 1 or 2 units. Let us say some arbitrary value. Let me shift by n time units. 1, 2. No, let us take simple example. Why do we bring some complexity here? Let me delay by 2 units of time. Okay, so 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6, and n. Again give to the same discrete time system. Now the input is delayed by 2 units, x of n minus 2. So what you expect from the output of the system is the same output but delayed by 2 units. Let us say this is 1, 0.75, 0.5, 0.25. So 0, 1, and it is 2 units, then 0.75, 0.5, 0.25, 2, 3, 4, 5. So this is your y of n, n minus 2. This y of n minus 2 is the same as delayed by by delayed by 2 units of this waveform. Therefore, the system is time invariant system. So, the same output is translated along the x axis by 2 units. In general, it will be n unit. Okay. So, that is how the response will be occurring at occurring for a shifted input signal. So, as you can see, this particular property will be very useful when you want to superpose the responses due to different inputs. Okay, we will use this property later. So, that is all for time invariant system. Then for time varying system, as I said, for continuous time, if time varying system cannot have this kind of property. Okay, for time variable system, if x of t gives rise to y of t, then x of delayed version of t, x of t, t will not necessarily gives rise to y of t minus td. So, you cannot say anything about it unless you know the actual behavior of the variable with respect to time. So, you should know the behavior of the system at that particular time, because it is changing time to time. Okay. So, now let us take some example for time varying and time invariant systems. Couple of examples. With that, we will stop this lecture. Consider the continuous time system defined by y of t is equal to sine of x of t. That means what? You have a CT system, continuous time system, and the input is x of t, but the output is sine of x of t. Now, we wanted to know whether the system is time invariant or time varying system. So, to check that the system is time invariant, we must determine whether the time invariance property holds for any input and any shift, any time shift. So, first you give x of t, then it gives rise to sine of x of t. Now, you consider another signal x of t minus, let us say, some delay. Okay, I mean td, sorry, I should be consistent with my notation, x suffix d. Okay, let me call this signal, let us say this is x1 of t. So, this is x1 of t. So, you delay the input x1 of t by td units. Let me call that is x2 of t. Now, if I give x2 of t, that gives rise to sine of x2 of t, right. Now, what is x2 of t we defined? We said x2 of t is x1 of t minus d. Therefore, sine of x1 of t minus td. Okay. Now, if you replace the t by td, then check out whether you are getting this and that. So, compare this equation and this equation. In equation 1, you replace t by t minus td. By the way, what is this? This is output of the system when input is x1 of t, that is x1 of t gives rise to y1 of t. What is y1 of t? Sine of x1 of t minus td. Now, replace y1 of t by d units. T minus td is equal to sine of t minus td. Now, compare this and that. Both are same, one and the same. Therefore, the system is time invariant system. Okay, it's very simple. So what you are doing is you take x1 of t and it gives rise to y1 of t, and you take x2 of t, it gives rise to y2 of t. Okay, where y1 of t is sine of x1 of t, that's it. So this is, let's say, equation number 1. Then we defined x2 of t is the time delayed version of x1 of t minus td. Let me call this as equation number 3. Therefore this is sine of x2 of t. Substitute let's say equation number 2, this is, let's say this is 3. Substitute 2 in 3. So you will get sine of x1 of t minus td. So this is my equation number 4. Now from equation 1, what you do is y1 of t is equal to sine of x1 of t. Now replace t by t minus td in equation 1. Therefore y1 of t minus td is equal to sine of x1 of t minus td. Let me call this is equation number 5. Now compare this and that, 5 and 4, both are similar, both are equal. Therefore the system is time invariant. Let me take one more example. Let's say y of n is equal to n times x of n. By looking at the equation itself, you can say this is time varying system, because there is a time dependent parameter n here. Okay, so this is a time varying system. So it can be verified very easily through the same procedure what we did in the previous case. Like you take x1 of n, it gives rise to y1 of n, and that y1 of n is equal to n times x1 of n. Now let's say this is equation 1. Then define x2 of n, which is delayed version of x1 of n. So n minus, let's say, some n suffix 0. Okay, now x2 of n you apply to the system, you will get y2 of n. y2 of n is n times x2 of n. Now what is x2 of n? x1 of n minus n naught. Let me say this is equation number 2. Sorry, this is 2, and this is 3, and this is 4. So in this step you substitute equation 2 in equation 3. So you will get n times x1 of n minus n naught. This is your y2 of n. Let me say this is equation number 4. Now let's take a 1. What is 1 says? Delay the output now. The next step is delay the output. If you delay the output, that is y1 of n is equal to n times x1 of n. Replace n by the same delay n naught. So you are delaying the output side now, n by n naught. Therefore y of n minus n naught, y1 of n minus n naught from equation 1 is equal to n will be replaced by n minus n naught times x1 of n, where n will be replaced by x1 of n minus n naught. Now let's say this equation number 5. Now compare 4 and 5, they are not equal. Therefore the system is time varying system. That's all. Okay. Let me consider one more example. I have a system. Input is x of t. Now I have continuous time system, and the output is y of t, and this y of t is x of 2t. When I say 2t, what does it mean? It means the input is time compressed. Therefore y of t is a time compressed version of x of t by a factor of 2. Okay, so in totally the system is, you can prove that this is time varying system. You can prove this, you can take some simple example and you can prove it. Let's say my input is like this. So minus 2 plus 2, this is 0, this is my t. Let's say this is x1 of t. Now if you give x1 of t to the system, CT system, then my output is y1 of t. That y1 of t will be compressed version of the input by a factor of 2. So therefore it looks like this, minus 1 to plus 1. Let me say this is y1 of t. Now what you do, delay this guy by some time units, delay by some time unit, say 2 units for example. You can take anything which you like. If you delay by 2 units, then now instead of starting at minus 2, now it starts at 0. 1, 2, 3, 4 boxes. So now it starts from 0 and it goes up to 4. Let me call this is x2 of t. x2 of t is equal to delayed version of x1 of t by how many units? 2 units, t minus 2. Now give this signal to the same system. Now the output will be, now it is compressed by 2 units. So it is going to be like this, 0 and 2. Let me call this is y2 of t. Now this y2 of t should be the same as delayed version of delayed version of what? This guy. Okay, so take this guy y1 of t. So next step is take y1 of t, then delay by 2 units. Because input is delayed by 2 units, so you delay the output also by 2 units now. If you do that by 2 units, then this minus 1 becomes plus 1, right? Look at here, this minus 1 comes to plus 1 and this plus 1 will go to 3. So therefore the delayed version looks like this, 1, 2, 3. Now are they equal, this and that? They are not. Therefore this shows that a time compressed version of an input is a time varying system. Okay, so the output time shift is only half as big as it should be for time variance. Therefore, due to the time compression imparted by the system, the system is time varying system. So let me stop at this point. Okay, thank you very much.